Imagine a cosmic drain, a place where gravity is so strong, not even light can escape. Right now, at the very heart of our own Milky Way galaxy, such a beast lurks. We call it Sagittarius A*, and it's about as massive as 4 million suns, all squished into a space smaller than Mercury. We can't see it directly, but we can see the chaos it creates, like a cosmic whirlpool pulling in stars and gas. Stick around, and we'll dive into the mind-bending reality of this supermassive black hole and what it means for you and me, right here on Earth. The galactic heartbeat. Our galaxy's center is a place of intense activity, a cosmic engine room where a supermassive black hole, Sagittarius A*, resides. This isn't just any black hole. It's the gravitational heart of the Milky Way, a point of immense density that pulls everything towards it. Imagine a cosmic vacuum cleaner, but on a scale so vast it dwarfs anything we can comprehend. This gravitational pull is what keeps stars, gas, and dust in their orbits around the galactic core. The galactic heartbeat isn't a literal sound, of course. Instead, it refers to the rhythmic pulses of energy and matter ejected from the vicinity of Sagittarius A*. Think of it like a heart pumping blood, but instead of blood, it's bursts of radiation and high-speed particles. These ejections happen periodically, influencing the surrounding interstellar medium. Sometimes, these pulses are like strong beats, pushing material outwards with great force. Other times, they are softer, more like gentle thumps. Scientists observe these energetic events by looking at the 10th rays and radio waves emitted from the black hole's neighborhood. When matter falls towards Sagittarius A*, it heats up to incredible temperatures, creating these emissions. These fluctuations in brightness and energy output are what we interpret as the galactic heartbeat. It's a constant reminder that even at the center of our seemingly calm galaxy, there's a powerful, dynamic force at play, shaping the cosmic landscape around it. This central engine doesn't just affect its immediate surroundings. The energy released by these heartbeats can travel vast distances, influencing star formation and the movement of gas clouds throughout the Milky Way. It's a complex feedback loop where the black hole's activity can both trigger and suppress the birth of new stars. So, while we can't hear it, the galactic heartbeat is a fundamental rhythm that dictates much of the galaxy's evolution, a silent but powerful pulse from our cosmic core. Our galactic neighborhood. Imagine our Milky Way galaxy as a giant cosmic city. Right at its heart, in the very center, lurks something incredibly powerful and mysterious, a supermassive black hole named Sagittarius A*. It's like the city's ultimate, inescapable drain, but instead of water, it swallows light and anything else that gets too close. This isn't just a tiny speck. It's 4 million times the mass of our sun packed into a surprisingly small space. Think of cramming all the elephants in the world into a single thimble. That gives you a hint of the density involved. This central black hole isn't alone in its neighborhood. It's surrounded by a bustling crowd of stars, gas, and dust. These stars are zipping around Sagittarius A* at incredible speeds, like tiny race cars on a cosmic track, held in orbit by its immense gravity. Some of these stars are ancient, having witnessed eons of galactic evolution, while others are younger, still forming in the chaotic environment. It's a dynamic and violent place, a stark contrast to the calmer spiral arms where our own solar system resides. The region around Sagittarius A* is often called the galactic center, and it's a hub of intense activity. Powerful magnetic fields swirl through the gas, creating spectacular radio emissions that we can detect with our telescopes. Think of it like a cosmic lighthouse, but instead of visible light, it's broadcasting radio waves from the extreme conditions near the black hole. This area is also where new stars are born, despite the harsh environment, in giant clouds of gas and dust that are being squeezed and heated. Our own solar system is located in one of the galaxy's spiral arms, far from the galactic core. We're about 26.0 light-years away from Sagittarius A*, which is a safe distance. It's like living in a quiet suburb compared to the bustling, sometimes dangerous, downtown of the galaxy. This distance means we are protected from the most extreme effects of the supermassive black hole, allowing life on Earth to flourish in relative peace. What is a black hole? A black hole is essentially a cosmic vacuum cleaner, but instead of dust bunnies, it sucks in anything that gets too close, including light itself. Imagine an incredibly dense object, so dense that its gravitational pull becomes overwhelmingly strong. This isn't just a little bit of gravity. It's like a bottomless pit in space. If you threw a ball up in the air on Earth, it would come back down because of gravity. But if you were near a black hole and threw a ball, it would just keep going and never return. The point of no return is called the event horizon. Once something crosses this boundary, there's no escaping, not even light, which is the fastest thing in the universe. That's why they're called black holes, because no light can get out for us to see them directly. Think of it like a super heavy bowling ball placed on a trampoline. The ball creates a deep dip in the fabric of the trampoline. If you roll a marble nearby, it will curve towards the bowling ball, and if it gets too close, it will fall into the dip and won't be able to roll out. A black hole does something similar to space-time, the fabric of the universe. Its immense mass warps space-time so severely that it creates this inescapable well. The singularity is the theoretical point at the very center of the black hole where all the mass is crushed into an infinitely small space. It's a place where our current understanding of physics kind of throws its hands up and says, "First, don't know what happens here." Black holes aren't just theoretical oddities. They are real cosmic phenomena. They form when massive stars reach the end of their lives. When a star much bigger than our sun runs out of fuel, it can collapse under its own gravity. This collapse is so dramatic that it squeezes the star's core down into an incredibly small and dense point. This is how stellar mass black holes are born. There are also supermassive black holes, which are millions or even billions of times the mass of our sun. These giants are found at the centers of most galaxies, including our own Milky Way. They likely grew over billions of years by gobbling up gas, dust, and even other stars. So, while we can't see a black hole directly because it swallows light, we can detect its presence by observing its effects on its surroundings. Imagine a drain in a sink. You can't see the drain itself if it's covered, but you can see the water swirling around it and disappearing. Similarly, astronomers can see stars and gas orbiting extremely fast around an invisible point in space, or they can detect the intense tinth rays emitted as matter heats up when it's being pulled into a black hole. It's like cosmic detective work, piecing together clues from the invisible to understand these powerful, enigmatic objects. The event horizon, a point of no return. The event horizon of Sagittarius A*, our galaxy's central black hole, is a boundary like no other. Think of it as the ultimate one-way street. Once anything, be it a star, a gas cloud, or even a brave and likely doomed astronaut, crosses this invisible threshold, there's no turning back. It's not a physical wall you can bump into. Rather, it's the point where the black hole's gravitational pull becomes so intense that not even light, the fastest thing in the universe, can escape. Imagine trying to swim upstream against a waterfall that's infinitely powerful. You're just going to get pulled over the edge. This point of no return is surprisingly small for such a colossal object. For Sagittarius A*, which has a mass about 4 million times that of our Sun, the event horizon would be roughly the size of Mercury's orbit. That might sound large, but in cosmic terms, it's a tiny target. Any matter or energy that ventures too close and crosses this boundary is destined to fall into the singularity at the black hole's heart, a point of infinite density where our current understanding of physics breaks down. It's like a cosmic drain where everything eventually disappears. The intense gravity near the event horizon also has some bizarre effects on spacetime. For an observer far away, time for an object approaching the event horizon would appear to slow down, eventually seeming to freeze just at the edge. However, for the object itself, time would continue normally as it plunges into the black hole. It's a mind-bending consequence of Einstein's theory of relativity, where gravity warps not just space, but time itself. This extreme warping means that even if you tried to send a radio signal back out to say hello, after crossing the horizon, that signal would be pulled back into the black hole along with you. Spaghettification, a cosmic stretch. Imagine an unfortunate astronaut, perhaps named Barry, getting too close to Sagittarius A*, our galaxy's supermassive black hole. As Barry drifts nearer, The gravitational pull on his feet becomes incredibly stronger than the pull on his head. This difference in gravitational force is the culprit behind a phenomenon astronomers call spaghettification. It's like stretching a piece of pizza dough, but instead of dough, it's berry, and instead of your hands, it's the immense gravity of the black hole. This cosmic stretching isn't a gentle pull, it's a violent distortion. The tidal forces, which are essentially the difference in gravity across an object, would begin to elongate Barry's body. His feet would be pulled harder and faster towards the black hole than his head, and his sides would be squeezed inwards. Think about trying to pull apart a very soft marshmallow. It stretches and thins out. Barry would experience a similar, albeit far more extreme, fate. The closer Barry gets, the more intense these tidal forces become. For a black hole as massive as Sagittarius A*, the spaghettification process would begin quite a distance away. It's not just about falling in. It's about being ripped apart long before even reaching the event horizon, the point of no return. The sheer gravitational gradient is so steep that it would overcome the structural integrity of any object, be it an astronaut or a star. This process is a stark reminder of the extreme physics at play around black holes. It's a cosmic ballet of destruction where gravity doesn't just pull, it tears. So, while we admire Sagittarius A* from afar, it's good to know that the universe has its own unique, and rather dramatic, ways of dealing with anything that gets too curious. Barry, poor Barry, would certainly have a story to tell, if only he could. Sagittarius A*, the monster in our midst. At the very heart of our Milky Way galaxy lurks a colossal enigma, a cosmic leviathan known as Sagittarius A*. It's not a fiery star, as its name might suggest, but a supermassive black hole, a region of space-time where gravity is so incredibly strong that nothing, not even light, can escape its pull. Think of it like a cosmic drain, but instead of water, it's sucking in anything that gets too close. This celestial monster is about 4 million times the mass of our Sun, a truly mind-boggling number that's hard to wrap our heads around. If you were to somehow compare its size to something familiar, it would be roughly the size of Mercury's orbit around the Sun. This gargantuan black hole isn't just sitting there idly. It's a dynamic entity influencing its surroundings in profound ways. Astronomers have observed stars orbiting Sagittarius A* at incredible speeds, zipping around it like race cars on a track, all held captive by its immense gravitational grip. These stellar orbits are like precise cosmic dance steps, allowing scientists to measure the black hole's mass and confirm its presence without actually seeing it directly. We can't see a black hole itself, just like you can't see the wind, but we can see the effects it has on the things around it, like leaves rustling or dust devils swirling. The intense gravity of Sagittarius A* also means that matter, when it falls in, gets incredibly hot and emits a torrent of radiation, including 10th rays. This is how we detect its presence and study its behavior. Imagine water being squeezed through a tiny pipe. It would build up pressure and heat. Similarly, as gas and dust spiral towards the black hole, they are compressed and heated to millions of degrees, creating a brilliant beacon that our telescopes can pick up. It's a violent, energetic process, a stark contrast to the quiet, unseen abyss at the black hole's center. While the idea of a supermassive black hole at our galaxy's core might sound alarming, it's important to remember that we are a safe distance away. Sagittarius A* is about 26.0 light-years from Earth, a cosmic chasm that prevents any immediate danger. Its influence is primarily felt by the stars and gas clouds in its immediate vicinity. So, while it's a powerful and mysterious force, it's more of a fascinating neighbor than an existential threat. It's like knowing there's a grumpy bear in the woods. You give it plenty of space and admire its power from afar. Discovery and early clues. For a long time, astronomers noticed that stars near the very center of our Milky Way galaxy were zipping around at incredible speeds. It was like watching a frantic dance, with these stars performing dizzying pirouettes. They were moving so fast, much faster than any normal star should, especially in a relatively calm region. This suggested that something incredibly massive and invisible was holding them in its gravitational grip. Think of it like a giant, unseen magnet pulling on tiny metal filings. the filings would fly around it at high speed. Scientists began to suspect that this cosmic dance was orchestrated by a supermassive black hole. But how do you find something that's, by definition, black and therefore invisible? It's like trying to find a perfectly camouflaged ninja in a dark room. You can't see them directly. The early clues weren't a direct sighting, but rather the effects of this unseen object on its surroundings. It was like seeing footprints in the snow and knowing someone walked there, even if you didn't see the person. One of the key pieces of evidence came from observing the radio waves emanating from the galactic center. There's a particular radio source, very strong and very compact, located precisely where astronomers suspected this massive object to be. This source, named Sagittarius A*, pronounced Sagittarius A*, was emitting radio waves that hinted at intense activity, the kind you'd expect from matter being squeezed and heated up before disappearing into a black hole's maw. It was like hearing a loud roar from behind a curtain, suggesting a powerful creature was present. Further observations tracked individual stars orbiting Sagittarius A* with remarkable precision. Over years, astronomers painstakingly mapped the paths of these stars. They saw them curve and loop, following orbits that could only be explained by a concentrated mass of something truly immense, packed into a tiny space. The math pointed to an object with the mass of millions of suns, all crammed into a region smaller than our solar system. This was the smoking gun, the undeniable evidence that a supermassive black hole, the undisputed king of our galaxy's center, was lurking there, pulling the strings of the cosmic ballet, weighing the unseeable. Figuring out how much something weighs when you can't even see it is a bit like trying to guess the weight of a ghost. That's essentially what astronomers have been doing with Sagittarius A*, the supermassive black hole lurking at the heart of our Milky Way. They can't directly put it on a cosmic scale, obviously. Instead, they've become detectives, observing the chaotic dance of stars and gas clouds swirling around this invisible giant. It's all about watching how fast things are moving and how tightly they're being pulled. Think of it like watching a merry-go-round. The faster the horses zoom around, the more massive the central pole must be to keep them from flying off. These celestial observations have revealed that stars near Sagittarius A* are zipping around at incredible speeds, some at a significant fraction of the speed of light. This frantic orbital ballet is the biggest clue. By meticulously tracking the paths and velocities of these stars, scientists can apply the laws of gravity, those same rules that keep our feet on the ground. It's a bit like watching a tiny pebble orbit a massive planet. The pebble's speed tells you a lot about the planet's mass, even if you can't see the planet itself. The closer the stars get to the black hole, the faster they have to go to avoid being gobbled up. Through these painstaking measurements, scientists have calculated that Sagittarius A* has a mass equivalent to about 4 million suns. That's a mind-boggling number, isn't it? Imagine stacking 4 million suns on top of each other. That's the sheer amount of stuff packed into this incredibly small region. This mass is concentrated into a space so dense that nothing, not even light, can escape its gravitational pull. It's like an ultimate cosmic drain, pulling everything towards its unseen center. The precision of these measurements has improved dramatically over the years, thanks to advanced telescopes and clever analytical techniques. It's a testament to human ingenuity, figuring out the weight of something so elusive. They've effectively weighed the unseeable by observing its powerful gravitational influence on everything around it. This isn't just an abstract cosmic curiosity. Understanding the mass of our galaxy's central black hole helps us understand how our entire galaxy formed and evolved. It's a key piece of the cosmic puzzle. The dance of stars around SGR A*, close to the heart of our Milky Way galaxy. A cosmic ballet is unfolding, a swirling vortex of stars performing an intricate dance around an invisible, colossal entity. This isn't your grandmother's waltz. It's a high-speed, gravitational tango orchestrated by Sagittarius A*, or SGR A* for short. Imagine a group of tiny, fast-spinning tops all circling a giant, unseen drain. That's a bit like what's happening out there, but with stars instead of tops and a supermassive black hole instead of a drain. These stars aren't just casually drifting. They're whipping around SGR-A asterisk at speeds that would make a race car driver dizzy, some completing a full orbit in mere decades. One of the most famous performers in this stellar ensemble is a star nicknamed S0-2. This particular star is like the prima ballerina, performing a very elliptical orbit, meaning it gets quite close to SGR-A asterisk at one point and then swings far away. When S0-2 makes its closest approach, it's moving at an astonishing 3% of the speed of light. That's like going from 0 to 60 in less than a blink of an eye, multiplied by millions. Its journey around SGR-A asterisk is so predictable, astronomers can map its path with incredible accuracy, almost like tracking a familiar comet across the night sky. The sheer gravitational pull of SGR-A asterisk is what dictates this celestial choreography. It's like an invisible puppeteer tugging on these stars with immense force, keeping them locked in their orbits. This pull is so strong because SGR-A asterisk is a supermassive black hole, packing the mass of about 4 million suns into a space roughly the size of our solar system. It's not a cosmic vacuum cleaner, though. Stars have to get quite close to be significantly affected. Think of it like standing near a powerful fan. You feel the breeze from a distance, but you only get really pulled in if you get right up to the blades. Observing this dance has been a remarkable feat of scientific ingenuity. For years, astronomers used powerful telescopes, like the Keck Observatory and the Very Large Telescope, to meticulously track the tiny movements of these stars over time. They've built up a detailed picture of the orbits, and by studying how these stars move, they can deduce the properties of the unseen object at the center. It's like figuring out what's inside a locked box by watching how objects outside the box are affected by its presence. This stellar ballet provides some of the most compelling evidence we have for the existence of supermassive black holes. Galactic cannibalism. Our Milky Way galaxy isn't a solitary diner. It's more like a cosmic hoarder, constantly grabbing snacks from its smaller neighbors. This galactic feasting is what astronomers affectionately call galactic cannibalism. Think of it like a giant, slow-motion Pac-Man gobbling up little dots. These dots are actually smaller dwarf galaxies that wander too close to our Milky Way's gravitational pull. When a dwarf galaxy gets too cozy, the immense gravity of the Milky Way starts to stretch and tear it apart. It's a bit like pulling a piece of taffy, but on a scale so vast it's hard to comprehend. Stars, gas, and dust are ripped away from the doomed galaxy, forming long streams that get incorporated into our own stellar collection. Evidence of this cosmic buffet can be seen in the faint trails of stars, called stellar streams, that arc through our galactic halo. These streams are like the leftover crumbs from a giant meal. One of the most famous victims of this galactic hunger is the Sagittarius dwarf spheroidal galaxy. It's currently being devoured by the Milky Way, its stars being pulled in and added to our own galactic disk. It's a process that's been happening for billions of years, and our galaxy is still very much in the mood for seconds. This ongoing consumption is a major way galaxies grow, especially the larger ones like ours. This isn't a violent, explosive event in the way we might imagine. Instead, it's a gradual, inexorable process driven by the fundamental force of gravity. The smaller galaxy doesn't even realize what's happening until it's too late, slowly being disassembled and its material becoming part of a much larger entity. It's a stark reminder that in the universe, size and power often dictate who gets to survive and who becomes part of something else. Black holes as cosmic engines. Our galaxy's supermassive black hole, Sagittarius A asterisk, isn't just a cosmic vacuum cleaner. It's a colossal engine that can power some of the most energetic phenomena in the universe. Think of it like a tiny, extremely dense water droplet that, when it falls into a drain, creates a powerful vortex. Sagittarius A asterisk does something similar, but on a galactic scale. As gas and stars spiral towards it, they don't just disappear. Instead, they heat up to incredible temperatures, forming a swirling disk called an accretion disk. This disk is like a giant, superheated frisbee, radiating immense amounts of energy. This energy isn't just light and heat. Sometimes, magnetic fields around the black hole get twisted and tangled, like a giant rubber band being wound up. When these fields snap, they can launch powerful jets of charged particles, moving at nearly the speed of light. out into space. These jets can stretch for thousands, even millions, of light years, far beyond the confines of our galaxy. It's like a cosmic particle accelerator, but the particles are going way faster than anything we can build on Earth, and the energy involved is mind-boggling. These jets aren't just pretty light shows. They can influence the entire galaxy. They can heat up the gas in the galaxy, preventing it from cooling down and forming new stars. This means the black hole, in a way, regulates star formation. It's a bit like a cosmic thermostat, keeping the galaxy from getting too crowded with new stellar nurseries. So, while it might seem like black holes are just destructive forces, they also play a crucial role in shaping the evolution of galaxies, acting as powerful engines that drive cosmic processes. Gravitational waves, ripples in spacetime. Imagine spacetime as a giant, invisible trampoline. When massive objects, like stars or planets, sit on it, they create a dip. Now, picture something truly colossal, like the supermassive black hole at the center of our Milky Way galaxy, Sagittarius A star. Its immense gravity is like a bowling ball placed dead center on that trampoline. Anything that gets too close, like a smaller star or even another black hole, will cause a much bigger disturbance. These disturbances aren't just static dips. They're dynamic, propagating outwards like ripples on a pond after you skip a stone. These ripples are gravitational waves. They are literally stretches and squeezes of spacetime itself, traveling at the speed of light. Think of it like this. If you jiggle the trampoline violently, the waves you create will spread out. That's essentially what gravitational waves are, just on a cosmic scale and made of the fabric of the universe. When incredibly energetic events happen near Sagittarius A*, such as two black holes merging or a star getting gobbled up, they send out colossal waves. These events are so extreme that they can warp spacetime significantly. These cosmic tremors, these gravitational waves, carry information about their violent origins. They're like cosmic Morse code, telling us about the cataclysmic events that generated them. Detecting these waves is a monumental feat. They are incredibly subtle, like trying to hear a whisper in a hurricane. Scientists use extremely sensitive instruments, like LIGO and Virgo, which are essentially giant L-shaped rulers designed to detect the minuscule stretching and squeezing of spacetime as a gravitational wave passes through. It's a bit like trying to measure a change in the distance between your house and the moon by the width of a human hair. But when these waves emanate from the vicinity of Sagittarius A*, they offer a unique window into the most extreme environments in our galaxy. The shadow of the black hole. The supermassive black hole at the heart of our Milky Way galaxy, Sagittarius A*, casts a shadow, a phenomenon predicted by Albert Einstein's theory of general relativity. This shadow isn't like the shadow you see from a street lamp on a wall. It's more like a dark silhouette against the bright, swirling gas and stars that surround the black hole. Think of it like looking at a distant, intensely bright light bulb, and then holding your hand up in front of it. Your hand blocks some of the light, creating a dark shape. In the case of Sagittarius A*, it's the black hole itself, with its incredibly strong gravity, that warps spacetime so much that light rays passing too close are bent away, creating this shadow. This cosmic shadow is incredibly small compared to the black hole's event horizon, the point of no return. The event horizon is the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. The shadow we observe is actually a region slightly larger than the event horizon. Imagine trying to get a clear picture of a tiny, fast-moving fly buzzing around a powerful spotlight in a dark room. It's incredibly difficult to discern the fly's exact edges, but you can see a general area where the light is obscured. Scientists use sophisticated telescopes, like the Event Horizon Telescope, to capture this elusive shadow. These telescopes work together, acting like a single, Earth-sized observatory, to achieve the resolution needed to see something so minuscule in the vastness of space. The first direct image of Sagittarius A*'s shadow, released in 2022, provided stunning confirmation of theoretical predictions. It looked remarkably similar to the shadow of the black hole at the center of the galaxy Messier 87, imaged a couple of years prior. This similarity is not a coincidence. Both are supermassive black holes, and while they have different masses, the physics governing their shadows are the same. The shadow's size is directly related to the black hole's mass, and its darkness is a testament to the intense gravity that bends light. It's like seeing two different sized donuts, but knowing they are both made from the same basic donut recipe. Observing this shadow allows scientists to test the limits of Einstein's general relativity in extreme gravitational environments. It's a way to probe the very fabric of space-time where gravity is at its most powerful. By studying the shape and size of the shadow, astronomers can learn more about the black hole's mass, spin, and how it interacts with its surrounding environment. It's a bit like a detective examining a footprint to understand the creature that made it. The shadow is a cosmic clue, offering valuable insights into these enigmatic objects that reside at the centers of galaxies. Imaging the invisible. Peering into the heart of our Milky Way galaxy is like trying to see a tiny, dark speck in the middle of a bustling city at midnight, all while wearing sunglasses. That speck is Sagittarius A*, our supermassive black hole. It's a cosmic vacuum cleaner so powerful that not even light can escape its grasp. So, how do we even know it's there, let alone get a glimpse of its surroundings? We can't just point a regular telescope and say, there it is. It's the ultimate hide-and-seek champion. Scientists have gotten incredibly clever, using a technique that's a bit like eavesdropping on a conversation happening in a very noisy room. They listen for the subtle whispers of matter swirling around the black hole, getting heated up and emitting tinth rays before taking the plunge. Think of it like hearing the sizzle of a burger on a grill, even if you can't see the burger itself. These tinth rays, though invisible to our eyes, are like cosmic Morse code, telling us about the extreme conditions near Sagittarius A star. It's a bit like trying to figure out what someone is eating by the crumbs they leave behind, but on a galactic scale. Then, there's the incredible feat of using interferometry. This is where multiple telescopes, spread across vast distances on Earth, work together like a giant, invisible eye. They combine their signals, effectively creating a telescope as big as the distance between them. It's like having a dozen friends, each with a tiny piece of a jigsaw puzzle, and by putting all their pieces together, you can see the whole picture. This has allowed us to capture the first ever images of the shadow of Sagittarius A*, a dark silhouette against the glowing gas that's about to be devoured. It's a ghostly outline, a testament to the black hole's immense gravity bending light around it. This shadow is our closest look yet at the event horizon, the point of no return. These images are not just pretty pictures. They are crucial pieces of evidence confirming Einstein's theory of general relativity. The way light bends around the black hole, creating that dark shadow, matches the predictions made over a century ago. It's like seeing a magic trick performed exactly as the magician described it, proving the underlying principles are sound. We're essentially using the universe's most extreme environments to test our fundamental understanding of physics, all by learning to see the invisible. The fate of matter falling in. Imagine a cosmic drain, but instead of water, it's stars, gas, and anything else that ventures too close. This is essentially what happens to matter that succumbs to the immense gravitational pull of Sagittarius A*, the supermassive black hole at the heart of our Milky Way. It doesn't just vanish. It embarks on a dramatic, one-way journey. As objects approach this point of no return, called the event horizon, they are stretched and squeezed like cosmic taffy. This process, known as spaghettification, is a direct consequence of the black hole's gravity being significantly stronger on the side of the object closer to it than on the farther side. Think of it like trying to pull a rubber band apart. The ends move away from each other with increasing force. For a star, this means it's literally torn into long, thin streams of plasma. It's a rather unceremonious end. Once this shredded material crosses the event horizon, its fate is sealed. It's like stepping off a waterfall. There's no turning back, and the destination is a mystery wrapped in an enigma. Inside the event horizon, space and time become so distorted that all paths lead inevitably towards the singularity, the infinitely dense point at the black hole's center. We can't see what happens there because no information, not even light, can escape. It's a bit like trying to get a postcard from a black hole. Impossible. The matter essentially ceases to exist as we understand it, its mass contributing to the ever-growing bulk of the black hole. However, before matter is completely consumed, a significant portion of it doesn't go down without a fight. As gas and dust spiral inwards, they form an accretion disk, a superheated, swirling vortex of material. This disk can become incredibly bright, emitting vast amounts of tinth rays and other radiation as friction heats the particles to millions of degrees. This is how we can detect and study black holes, by observing the energetic fireworks happening just outside their event horizons. Sometimes, this swirling matter gets so agitated that some of it is ejected outwards in powerful jets of particles moving at nearly the speed of light. It's like the black hole is burping out some of the stuff it can't quite digest, a spectacular cosmic expulsion. So, while the ultimate destination for matter falling into Sagittarius A** is the singularity, the journey there is anything but simple. It's a violent, fiery spectacle, a testament to the extreme physics at play in the universe's most enigmatic objects. The material gets ripped apart, heated to unimaginable temperatures, and some of it is even blasted back out into space before the rest is irrevocably lost to the black hole's insatiable hunger. It's a cosmic recycling program with a very dramatic twist. Black holes and galaxy evolution. Supermassive black holes, like the one lurking at the heart of our own Milky Way, Sagittarius A*, aren't just cosmic vacuum cleaners. They're actually quite influential in shaping the galaxies they inhabit. Think of a black hole as the ultimate cosmic chef, and the galaxy as its kitchen. The chef's actions, like stirring the pot or adding ingredients, dramatically affect the final dish. These galactic giants influence galaxy evolution by affecting the gas and dust within their host galaxies. When matter falls towards a supermassive black hole, it doesn't just vanish. Instead, it forms a superheated disk called an accretion disk. This disk gets so hot that it emits enormous amounts of energy, including powerful jets of particles that can shoot out at nearly the speed of light. These jets can push surrounding gas away, acting like a cosmic broom. This process can prevent new stars from forming, essentially putting the brakes on star birth in the galaxy. It's like the chef accidentally burning a batch of cookies and having to clean up the mess before starting a new one. Furthermore, the gravitational pull of the supermassive black hole itself plays a role. It can influence the orbits of stars and gas clouds near the galactic center, potentially triggering star formation in some regions while suppressing it in others. Imagine the black hole as a cosmic DJ, its gravitational tunes dictating the dance moves of the stars and gas. Sometimes its rhythm encourages a star-forming party, and other times, its powerful bass line scatters the dancers. This interplay between the black hole's feeding frenzy and its gravitational influence helps sculpt the galaxy's structure over billions of years, determining how many stars it will have and how they'll be arranged. Are there other black holes in the Milky Way? Our galaxy, the Milky Way, is a vast cosmic city, and while we know about the supermassive black hole, Sagittarius A*, chilling at its heart, the question arises, are there other black holes lurking in our galactic neighborhood? The answer is a resounding yes. Scientists estimate there could be anywhere from 10 million to 100 million stellar mass black holes scattered throughout the Milky Way. These aren't the gargantuan monsters like Sagittarius A*. Instead, they are the dramatic finales of massive stars. When a star much bigger than our sun runs out of fuel, it collapses under its own gravity, and if it's heavy enough, it implodes into a black hole, a point of no return where gravity is so intense that not even light can escape. Think of it like a cosmic drain, but instead of water, it's sucking in anything that gets too close. These stellar mass black holes are incredibly difficult to spot because, well, they don't emit light. It's like trying to find a ninja in a dark room wearing black pajamas. However, astronomers have developed clever ways to detect their presence. One common method is by observing their gravitational influence on nearby stars or gas. If a star is orbiting something invisible, and that something is incredibly massive, it's a strong clue that a black hole might be the culprit. Sometimes, a black hole can pull gas from a companion star, creating a swirling disk of superheated material around it. This disk glows brightly in tinth rays, acting like a cosmic beacon that astronomers can pick up with special telescopes. It's a bit like spotting a tiny, incredibly bright firefly in the vast darkness of space. Another way we find them is through gravitational waves. Remember those ripples in space-time that Einstein predicted? When two black holes collide, or a black hole and a neutron star merge, they create these powerful waves. Think of it like dropping two pebbles into a still pond. You see the ripples spread outwards. Detecting these gravitational waves, first achieved in 2015, has opened up a whole new window into the universe and confirmed the existence of many more black holes than we could previously observe. These events are rare, but they provide undeniable proof of these dark, enigmatic objects. So, while Sagittarius A** is the undisputed king of our galaxy's center, it's just one of potentially tens of millions of black holes that call the Milky Way home. They are remnants of stellar death, hidden in plain sight, influencing their surroundings through gravity, and occasionally announcing their presence with spectacular cosmic fireworks. The universe, it seems, is far more populated with these dark entities than we might initially imagine. The mystery of dark matter. Around the supermassive black hole at the heart of our Milky Way, known as Sagittarius A*, something peculiar is happening. The stars and gas clouds are orbiting this central point much faster than they should, given the visible matter we can detect. It's like watching a merry-go-round spin at breakneck speed, but you can only see a few horses attached. Where's the rest of the mass that's making everything whip around so quickly? Scientists have a name for this unseen gravitational influencer: dark matter. It's not dark in the sense of being black or shadowy. It's dark because it doesn't interact with light. It doesn't absorb it, reflect it, or emit it, making it utterly invisible to our telescopes. Think of it as the ultimate introvert of the universe, shyly lurking in the background, exerting its presence purely through gravity. We know it's there because of its gravitational pull, much like you know the wind is blowing even though you can't see the air itself. This invisible stuff makes up an astonishing amount of the universe's mass, far more than all the stars, planets, and gas clouds combined. In fact, estimates suggest dark matter accounts for about 85% of all matter in the cosmos. So, that black hole at our galaxy's center? It's probably surrounded by a massive halo of this mysterious substance, providing the extra gravitational oomph to keep those fast-moving stars in their orbits. It's this invisible scaffolding that shapes galaxies and dictates how they evolve. The exact nature of dark matter remains one of the biggest puzzles in modern physics. Is it made of exotic particles we haven't discovered yet, like WIMPs, weakly interacting massive particles? Or could it be something stranger, like tiny, invisible black holes formed in the early universe? Researchers are building incredibly sensitive detectors deep underground, shielded from cosmic rays, hoping to catch a fleeting glimpse or interaction of these elusive particles. It's a cosmic scavenger hunt, trying to find something that, by definition, doesn't want to be found. The ultimate fate of black holes. The ultimate fate of black holes is a slow, drawn-out process, not a dramatic explosion. Think of it like a very, very slow leak. These cosmic vacuum cleaners, while incredibly powerful at gobbling up matter, aren't actually eternal. They lose mass over unfathomably long timescales through a phenomenon called Hawking radiation. It's a bit like a black hole sweating tiny particles, a process so gradual that even the smallest black holes we know of would take far longer than the current age of the universe to evaporate completely. For a supermassive black hole, like Sagittarius A*, the one lurking at the heart of our Milky Way, the evaporation process is so mind-bogglingly slow it's essentially a theoretical concept for now. To grasp the timescale, imagine trying to empty an Olympic-sized swimming pool with an eyedropper. That's roughly the speed at which a stellar mass black hole loses mass. Now, picture Sagittarius A*, which is millions of times more massive than our Sun. Its evaporation time is so immense it makes the lifespan of stars look like a fleeting blink. Scientists calculate this could take something like 10⁻100 years, a number so large it has more zeros than there are atoms in the observable universe. So, while theoretically they do fade away, for all practical purposes, they're here to stay for an incredibly long time. The process of Hawking radiation is a bit quirky. It suggests that at the edge of a black hole, the event horizon, pairs of particles and antiparticles can spontaneously pop into existence. Usually, they annihilate each other instantly. But sometimes, one particle falls into the black hole while the other escapes. The escaping particle carries away a tiny bit of energy, which, from the black hole's perspective, means it has lost a tiny bit of mass. It's like the black hole is paying a cosmic toll for every particle that escapes its gravitational grasp. So, what happens at the very end? As a black hole shrinks, its Hawking radiation intensifies. Towards the final moments, it would radiate furiously, releasing a burst of energy. It's the universe's ultimate fizzle, not a bang. But again, this is for the theoretical evaporation of a black hole. The black holes we observe today, especially the supermassive ones, are far from this final stage. They are still actively growing, consuming gas, dust, and even stars, making them formidable objects in the cosmos for the foreseeable future. Beyond Sagittarius A*, the region surrounding our galaxy's supermassive black hole, Sagittarius A*, is far from empty. Instead, it's a chaotic ballet of stars, gas, and magnetic fields, all whipped into a frenzy by the immense gravitational pull. Think of it like a cosmic roundabout, but instead of cars, you have stars whizzing around at speeds that would make your head spin, and not just a little bit. Some of these stars are so close to Sagittarius A* that they complete an orbit in mere decades, a blink of an eye in astronomical terms. We can actually track their movements, like cosmic paparazzi capturing the ultimate celebrity dance. What's truly fascinating is the extreme environment these stars endure. Imagine standing next to a giant vacuum cleaner that's also a supernova. That's kind of what it's like for these stellar survivors. They're constantly being buffeted by powerful magnetic fields and bathed in intense radiation. Yet, many of them are still there, a testament to their resilience. Scientists are particularly interested in these S-stars, as they're called, because their orbits provide a unique laboratory for testing Einstein's theory of general relativity in its most extreme form. It's like a real-life physics experiment, but with much higher stakes and way more explosions. Beyond the immediate vicinity of the black hole, things get even more interesting. We find a dense cluster of stars, a stellar metropolis packed much tighter than anywhere else in the galaxy. This nuclear star cluster is a swirling vortex of stellar activity, with stars colliding, merging, and generally making a lot of noise. It's the galactic equivalent of a crowded city center, but instead of honking horns, you have stellar winds and gravitational tugs. Within this cluster, there's evidence of even more exotic objects, like stellar remnants and possibly even intermediate mass black holes, although these are still subjects of intense study and debate. The gas and dust in this region are also behaving in peculiar ways. Instead of being smoothly drawn into the black hole, some of it gets flung outwards in powerful jets. These jets are like cosmic water fountains, but instead of water, they're spewing out superheated particles at near light speed. These jets can extend for thousands of light years, influencing the surrounding galaxy. It's a dramatic display of power, showing that even a black hole, which is supposed to be a devourer, can also be a source of immense energy and cosmic sculpting. So, there it is, Sagittarius A*, our supermassive black hole, quietly munching away at the galactic center. It's like the ultimate cosmic hoarder, gobbling up stars and gas, but thankfully, it's too far away to cause us any real trouble. Think of it as that one neighbor who has a really loud party, but it's across town. You hear about it, but you're not directly affected. It's a reminder of the incredible, and sometimes a little scary, forces shaping our universe. What else is lurking in the cosmic shadows? Next time, we're diving into the mind-bending world of dark matter, the invisible stuff that holds galaxies together. Don't miss it.